Hello. So I'm going to deal with earthquake analysis, equivalent static method or seismic coefficient method. So let me start. Now, referring to IS 1893 Part 1 2016, that is criteria for earthquake resistant design of structures. Now, there are few methods of obtaining lateral forces for buildings. That is, first is equivalent static method, which is also called as seismic coefficient method, and second is dynamic analysis, under which again there is response spectrum method and there is time history method. So let us briefly see about what is seismic coefficient method. This method simplifies the dynamic loading into an equivalent static load. Now the applications are, it is based on the concept of a static load that would produce the same maximum response, that is displacement forces, as produced by the actual dynamic loading. Now the usage is, it's commonly used for structures with predictable behavior and when the dynamic effects are not very complex. It often employs a response modification factor to account for inelastic behavior of the structure. However, there are certain shortcomings or limitations of this equivalent static method. It may not be accurately capturing the response for highly irregular structures or the structures with significant dynamic characteristics. Again, it neglects higher modes of vibration and also it neglects non-linear behavior and soil structure interaction. So let me go further. Now this equivalent static analysis is well suited for the analysis of structure which is having approximate natural period Ta less than 0.4 second. Now if we refer the IS code clause 7.6.2, it is given that the approximate fundamental translational natural period Ta of oscillation in seconds is given for three categories. That is A, bare moment resisting frame buildings without any masonry infills, that means without any walls. Then buildings with reinforced concrete structural walls, and category C they have made for all other buildings. Now let me demonstrate seismic coefficient method by one simple and fundamental problem. A 4-story RCC framed hospital building is located in seismic zone 4 of India. The floor to floor height is 3 meter as shown here. The building rests on hard rock, so the foundation is resting on hard rock. Now the dead load plus imposed load which is lumped at the floor is 3200 kilonewton. That means we can see at floor 1, 2 and 3 the lumped mass is 3200 kilonewton, whereas the dead load plus imposed load which is lumped at the roof, that is R4, is 2700 kilonewton. Now consider bare RCC frame without any infill walls. That means without any walls, only you have to consider the frame structure, and the question is find the total base shear as well as the lateral force at each floor. Now let us assume that it is having spatial moment resisting frame structure, there is SMRF, and therefore response reduction factor from table 9 of IS code is for category B, that is RC buildings with spatial moment resisting frame, is 5. Now here I am not going to discuss the theory about response reduction factor, so directly I am taking input R is equal to 5. Again, if we refer table 8 of IS code, then since it is a hospital building, therefore importance factor is 1.5. Again, it is given that the building is located in seismic zone 4 of India, and therefore if we refer table 3 of IS code, then for seismic zone 4 the seismic zone factor is 0.24. Now we already know that dead load and imposed load lumped at floors is 3200 kilonewton, whereas at roof it is 2700 kilonewton. So total seismic weight of this building is 3 times 3200 plus 2700. So the total seismic weight, that is 3 floors and one roof, it is 12300 kilonewton, that is 12,300 kilonewton. Now next step is to calculate the design lateral force, which is called as base shear. Now as per clause 7.6.2, the approximate fundamental translation natural period TA of oscillation second shall be estimated by the following expressions, that is A, bare moment resisting frames, buildings without any masonry fills, that means without any walls. So for that, for RC MRF buildings, TA is given as 0.075 h raised to 0.75, where h is the total height of the building. Therefore here approximate fundamental natural period is 0.075 into total height of the building is 12 meter, 12 raised to 0.75. So TA is 0.483 seconds. Now going further, again from the IS code, clause 6.4.2a says that for use in equivalent static method or seismic coefficient method, for rocky or hard soil sites, when TA is between 0.4 seconds and 4 seconds, which is our case, because here our TA is 0.483, we have calculated, then SA by G is given as 1 by TA. Here it is clearly shown here. This is I have taken from IS code directly. So 1 by TA. That means your SA by G is 1 by 0.483. So SA by G is 2.07. Now as per clause 6.4.2 of IS code, the design horizontal seismic coefficient AH is Z by 2 into this SA by G, that is acceleration, into I by R. So here Z, that is seismic zone factor, is 0.24 divided by 2. SA by Z is 2.07. Importance factor I is 1.5 and response reduction factor is 5. Therefore, we directly get AH, that is design horizontal seismic coefficient, as 0.07452. Again going to clause 7.6.1, the design base shear, that is shear force at the base of the building, VB is equal to H into W, that is design horizontal seismic coefficient into seismic weight. So when we multiply it, we get the shear force at the base, VB is 916.596 kilonewton. Now going further, when we see clause 7.6.3, the design base shear VB, which is computed in clause 7.6.1, shall be actually distributed along the height of the building and in plan at each floor level as below. A, the vertical distribution of base shear to different floor levels. The design base shear VB computed in 7.6.1 shall be distributed along the height of the building as per the following expression, that is QI is equal to WI HI square upon summation of I is equal to 1 to n WI HI square into VB, where QI is design lateral force at floor I, WI is the seismic weight of floor I, HI is the height of floor I measured from base, and then is the number of stories in building, that is number of levels at which the masses are actually located. So again this I have directly taken from the IS code, and therefore let us make this simple table, that is design lateral force at floor. Now here first floor level, we know that there are 3 floors and 1 roof, so there are 4 floors. Floor number 1, 2, 3 and 4th is a roof. Again WI kilonewton, that is the weight, so again 3200 up to floor 1, 2, 3, and for roof it is 2700. Then height from the base for floor 1 is 3 meter, floor 2 is 6 meter, floor 3 is 9 meter, and the height of roof is 12 meter. Now again here we need WI HI square. So simple, I will just take 2700 into 12 square. So that becomes 388800. Similarly, I will do it for all the remaining rows. Then design lateral force at floor I. QI, kilonewton. So when again I go back to previous PPT, QI is given by that individual WHI square divided by summation of WHI square into VB. So again here I have got it like this, that VB, that is 916.596 multiplied by this WHI square, that is 388800, divided by summation of WHI square, that is 792000. So I get this value 449.965 kilonewton. That is the design lateral force at floor I. Similarly, I will do it for remaining 3 rows, and the final column is story shear forces, that is cumulative forces VI. So here at the top, this one floor, that is roof, it will be same 449.965, because that is the top floor, there is no floor above that. So here I will just copy it here. Whereas for the next, that is for the third floor, it will be 449.965 plus 299.976. So that's why it is cumulative. So 749.941. Again for second floor it will be 749.941 plus 133.323, that is 883.264 kilonewton. And finally for the first floor it is 883.264 kilonewton plus 33.344, that is 916.60 kilonewton. So here again we got a cross check that whatever base shear we had calculated 916.596, again the answer is same. So it is distributed now correctly. Now this is how we can show it, I mean in a diagram. So this is a building, and here the base shear is 916.60 kilonewton, and the designed lateral force at each floor, here at first floor it is 33.344 kilonewton, second is 133.323, third is 299.976, and top it is 449.965 kilonewton. So here we can clearly observe that as the height of the building goes on increasing, our design lateral force at floor, it goes on increasing. Again we can show the story shear force as shown in this diagram on the right. So again it is 449.965, and then cumulative when we add, these are all the story shear forces. At the bottom it is maximum, that is 916.60 kilonewton. That means here we distribute the base shear into various story shear forces. And finally this is how we can present the lateral force at each floor. That means whatever I had shown in this previous PPT on this left diagram, that only I am just I mean pictorially I am showing here for better understanding. That is Q1, Q2, Q3 and Q4, that is lateral force at each floor as per this seismic coefficient method or equivalent static method. So this is what I wanted to convey. Thank you very much.